All right, so welcome back to the sequel on the paper. This is on the second paper of Maria, Sean, and Eugene, and a geometric interpretation of the delta conjecture. So Sean will be giving a series of three or maybe even four, probably four talks, and we'll turn it over to Sean.
Thank you. Um, yeah, thank you so much for letting us do these talks. We're very excited about this work. So yeah, let me so I regrettably I couldn't attend Maria's talks, but just to remind you what she was talking about was this direct relationship between the symmetric function in the rectangular irrational Shuffle theorem and the symmetric function in the delta theorem via this Schur skewing operator. And she gave an algebraic interpretation and using work of Blasiak, Heyman, Morse, Poon, and Seelinger and a combinatorial proof in terms of using a sign reversing involution. Um, and um, and throughout these talks, the goal is to use this identity to give a geometric interpretation of the delta conjecture or delta theorem side. Um, so I'll explain like what each side means in terms of affine Springer fibers, and what applying this kind of skew Schering operator means in terms of the theory of Borhon-McPherson's partial resolutions of nilpotent varieties, and how it all connects. Or hopefully that's my goal. Um, so. Um, So, an outline of the talks. The first talk today, I wanted to keep it light and very combinatorial. So, basically, you know, all three talks, I will probably have algebraic combinatorialists in mind as my main audience um, and try to give lots of examples. Um, and so, in this first talk, I wanted to um, just connect the combinatorics of the delta theorem side. But add a specialization of t equals 0, setting one of the parameters equal to 0, and then explaining what that has to do in terms of the geometry of two different spaces, one, the spanning line configurations of Pawlowski and Rhodes, and two, in terms of what I like to call the delta Springer fibers. Um, and the second talk will be kind of a crash course um, on Springer theory, um, and what it has to do with symmetric function theory, and explaining my understanding of Borhon-McPherson's theory of partial resolutions of nilpotent varieties. And then in talk three, tying all of that together and explaining how you can extend these partial resolutions to affine Springer fibers and use it to model all of this combinatorics. Okay. Um, so, yeah, probably the first talk will be the least technical, and maybe the second and third talks will be a bit more technical, but with combinatorics or algebraic combinatorialists in mind. Um, but there might be sometimes, say during the second talk, when I might make a side comment about perverse sheaves, for example, or the decomposition theorem. Um, Okay. So, starting from this combinatorial formula for the delta theorem, and this is the rise or fall version of the delta theorem. If you're aware of the other version, the valley version, it was proven by Dedary and Mellet, and independently by Blazia, Kamen, Morse, Poon, and Seelinger, and they proved different generalizations of this formula. That the delta operator, the delta prime operator applied to En gives you this beautiful combinatorial formula in terms of stacked word labeled stacked parking functions, keeping track of some inversion statistic and some area statistic and a monomial corresponding to the labeling. And for this talk, I want to simplify down so that we can really see or match it up with geometry in some way. So the first simplifying assumption I'll make is area 0. So for these stacked parking functions, you will have some path, and then some stack underneath. Um, and then the area is the number of cells in between the stack and the path. But for area 0, we'll have diagrams where the stack meets the path in each column. So something like this. Um, and then you have some increasing labeling up each column. Um, and the second simplifying assumption I want to make is to simplify down to polynomials rather than symmetric functions. So I will also assume that, so let me call that P. I'll also assume that the labeling is standard. So meaning that the labels are 1 through n, and I use each of those labels exactly once. Um, for example, maybe I'll draw the example down here. For n equals 5, k equals 3, we have 3 columns and 5 rows. And maybe this is my lattice path. And again, my stack meets the path in each column. And then I could have like 1, 3, 5, and 2, 4 increasing up each column. So that will be P. Um, so up here, I have my word labeled deep paths with some stack, and restricting to area 0 and P standard. And now to get at these two different kinds of geometry, these two different, or to translate this into geometry, I need two different bijections to two different kinds of objects. So the first bijection will be in terms of partial row strict labelings of a particular rectangle. So of the rectangle with these particular dimensions. Um, so with k rows and n minus k plus 1 columns. So let me call these row strict labelings nk. And there's a bijection between these two things, and maybe I'll write down the example and then explain more what I mean by this object. Um, so I take my stacked parking function and I draw my rectangle with 3 rows, k equals 3 rows, and then n minus k plus 1, which is also 3 in this particular example, many columns. And I'm just going to convert the columns into rows and write justify everything. So really, I'm kind of just right aligning everything and rotating. Um, and so what I mean by these objects is um, so that the labels decrease in each row. Um, and each row is non-empty. And the labels are right justified in each row. Um, so that's what I mean by row strict labelings. Um, and on the other hand, so those are in bijection. And on the other hand, we could convert these into, alternatively, we could convert these into what are called Fubini words. So these are Fubini words on the letters 1 through k, which is the set of words of length n, such that each label is each letter in the word is 1 through k, and we use each of those letters at least once. So put another way, let me give myself enough space. Put another way, the set of the labels 1 through W1 through W1 is equal to the set 1 through k. So in terms of my example down here, my word would be to get my word, I just read off the rows of the letters. And I think Maria had a comment. I don't remember what kind of Fubini word you gave, but it should be in bijection. Yeah, I don't remember exactly from the notes which definition you gave. Allowable content. Yeah, I'm not sure. So, I mean, this type of Fubini word, you label the rows 1 through 3, and or over here the columns 1 through 3. And to create a word, to create a word with length 5, you just read off, okay, the first letter is in the first column, so I put a 1. The second letter is in the third column, so I put a 3. Third letter is in the first column, so I put a 1, and so on. So fourth is in the third column, fifth is in the second column. And then, of course, there's an easy bijection between these two as well. Um, so let me check the chat again. Oh, okay. Yeah, we can work it out later together, maybe, Maria. Okay, so why did I introduce these bijections? It turns out that these two bottom sets naturally index torus fixed points of two particular varieties. So the first space is called the spanning configuration space of Pawlowski Rhodes. So given two integers n greater than or equal to k, they defined the space of tuples of lines in some fixed space. So Li is a one-dimensional subspace, vector subspace in C to the k, and such that the span of these n lines is the entire space. And so each of these lines is an element of projective space. So this is a subspace of the product, the n-fold product of pk minus 1. But then you can take this a tuple of lines and represent it maybe more concretely with a matrix. So point in this space can be represented by a k by n matrix, where you place a vector in each column such that the ith vector spans the ith line. So where Li is the vector space span of the ith vector. But not all matrices represent a point in the space. And these matrices are up to some equivalence, up to scaling the columns.
What is the
So
PK minus 1?
okay. So pk minus 1, pk minus 1 is so complex projective space. So it's the space of all one-dimensional. It's a space of all lines in C to the k. So dimension of L is 1.
Okay.
Some people write this as CP k minus 1, and the k minus 1 is because it's a k minus 1 dimensional space. Okay. Okay, so the properties of these matrices is that each column is non-zero. Otherwise, it wouldn't span a line, it would just span the zero vector. And this matrix is unique up to scaling the columns individually. But then, so that's just saying we have a tuple of lines, but then we have this extra spanning condition, which means that the matrix has to be full rank. And another way to say full rank matrix is that, or let me write that down. So the matrix is full rank because of the spanning condition, or equivalently, some k by k minor of the matrix is non-zero. And this condition, some k by k minor being non-zero, that's setting some polynomial to be not equal to 0, which is an open condition. So this is telling us that it's an open subspace, open subvariety of this product of projective spaces. In particular, it's not compact. It's a smooth space, but it's not a compact space, which will come up later. And so what did I mean at the top by torus fixed points? So let me explain the torus action and the fixed points. So the torus So we have a torus, which is the k-fold product of C star being, so C star, I mean the non-zero complex numbers, that it acts on this Pawlowski-Rhodes space on the left of the matrix, essentially. So an element in this torus could be, some length k tuple of non-zero complex numbers, and then the action is just using this this tuple to scale each line. Or sorry. So acting on this tuple of lines, you act on each individual line diagonally. Coordinate-wise. So yeah. So in terms of the matrix, and if you want to think about this in terms of the matrix, I'm just matrix multiplying on the left by the diagonal matrix with t's along the diagonal. And the torus fixed points are the set of tuples of lines that get fixed by this action. And I'll give an example. I'll give some examples in a second. And they're represented by matrices. Matrices that have exactly one non-zero entry in each column. So let me do an example. Let's say n equals 3 and k equals 2. Then the torus fixed points are all of the representative matrices that have this property. So for example, I could have this full rank matrix. So it represents a tuple of spanning lines. And the reason why it's a torus fixed point is because if I were to act on this on the left, by T1, T2, I would get a different matrix, but it would still represent the same tuple of lines. So this is, so up here I said the matrix is unique up to scaling columns, and you can unscale those T factors individually to get back to the same matrix. So same spanning line configuration. So some more examples. I could have 1, 0, and then 0, 1, 0, 1. So E1, then E2, then E1, or E2, then E1, then E1, or E2, E2, E1. And there's one more, which is E2, E1, E1. And you can check, those are all of the full rank matrices with only ones and zeros. Um, yeah, with one in each column, basically. So how do I think of these in terms of Fubini words? I can just take this matrix and record which row the one is in. So I could turn this matrix into into the Fubini word 1, 1, 2, the next one into 1, 2, 2, this one into 1, 2, 1, and then 2, 1, 1, 2, 2, 1, and then 2, 1, 2. Okay. Were there any questions on spanning configurations before I move on? Okay. So let me move on to the second geometric realization. So what I like to call delta Springer fibers, which will be kind of the main focus for some of the talks. And this one instead of in terms of lines, it'll be in terms of certain flags of vector spaces. So we'll define a nilpotent matrix acting on some large vector space, in particular of dimension equal to the size of that rectangle that I drew earlier. And essentially how I'll define this is by taking the rectangle with rows k and columns n minus k plus 1 and filling it in with basis vectors. So in the first column, I will insert E1, E2, dot, 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 up to EK, and then kind of wrap around labeling with basis vectors. So EK plus 1, ek plus 2, and so on, up to e2k. And so on and so forth, filling in this rectangle. So how do I use this to define a nilpotent matrix? So I'll declare that this nilpotent matrix moves everything to the right. So define how n acts on the basis vectors as n acting on I will move it one box to the right, which, since there are k things in each column, it'll just be subtracting k from the index. That's if if I is greater than k. So for example, ek plus 1 goes to e2, e2k goes to ek, and so on. But I still have to tell you what does it do to e1 through ek. I'll just let those map to 0. So somehow e1, e2, and so on fall off the diagram and go to 0. So n acting on e1 through ek are all 0. And the delta Springer fiber is defined to be a certain space of flags of vector spaces. So you start with, and it will be very reminiscent of the complete flag variety if you've ever seen that. So I'll start with a one-dimensional subspace. And then choose a two-dimensional subspace containing it, and so on, up to an n-dimensional subspace. So here, the dimension of subspace VI is I. And I'm going to impose two extra conditions. The first one is reminiscent of what's called a Springer fiber. So that's like the Springer fiber part of the name. That when I act by my nilpotent on the ith piece of the flag, I stay within the ith piece of the flag for each I. And one extra condition that Vn contains the kernel of n. So the kernel of n is just this first column. Yeah. So equivalently, you could say this condition is equivalent to saying E1 through EK are all in. Like when you end the flag, you've picked up all of the basis vectors E1 through EK. And so this space is contained in what's called the partial flag variety.
That should be VK.
V where?
You said E1 to EK in VN.
Yes, E1. So E1 through EN are the basis vectors in this column. And this is an n-dimensional space, and these are k vectors. And I'm just imposing this condition that like this k-dimensional space is contained in this n-dimensional space.
Okay.
And okay, so this is contained in the space of partial flags. So partial flag variety. By which I just mean the space of all nested sequences of subspaces without these extra conditions, or sorry, without these extra conditions. So these elements you can also realize in terms of matrices.
Hey, Sean,
Yes.
can I ask a quick question? Just,
Mhm.
in your partial fact variety indexing, why is the last one?
Oh,
Like,
sorry.
These should
Yeah,
add
that is,
up, they add up to something? Do they add up to K times N minus, I'm a little, okay.
no, I just wrote it down wrong. I should have subtracted n out of the total dimension.
Thank you, yeah.
Thank you. Um, okay, so each of these flags of subspaces can be represented by a matrix. In particular, k times n minus k plus 1 by n matrix. Where we take representatives of these subspaces. So it will be, so fill in the columns with v1 through vn, where v1 through vn are some vectors chosen so that the span of the first I vectors is the ith subspace in the flag. Okay. And yeah, and so these two conditions you can write down. So this condition you can write down in terms of matrix coordinates by, so this one, so such that the first condition you can write down as saying that if you were to take the first I vectors, the matrix containing the first I vectors, and then apply the nilpotent to the ith vector, sorry, let me just say, and then apply let me say it this way, and then apply the nilpotent to the first I vectors. So you need these vectors to be in the span of those vectors, and so it's a condition on the rank. The first I vectors are already give you a rank I matrix, so you impose the condition that the rank of this matrix is at most I. And then you can write that down in terms of minors. So equivalently, the I plus 1 by I plus 1 minors of this matrix vanish, are 0. So it's given by some polynomial equation, which gives you a closed condition on the space. So in fact, and you can interpret this condition as well in terms of equations on the matrix coordinates. So in fact, this is a closed subvariety of the partial flag variety. Okay, but let me get back to the combinatorics. So why define the space? It's because there's a torus action and its torus fixed points are in bijection with the other combinatorial objects I wrote down above. So we have a torus which acts on, sorry, I changed the name accidentally. Let me put a delta in this. So there's a torus action on the space by declaring that your torus element basically acts the same on each row. So if I hit this with, if I hit the basis vector I plus km, that's some vector in the ith row. And you scale it with the ith piece of that element. So kind of pictorially, T acts by T1 on all of these vectors in the first row and scales everything in the second row by T2, and so on. Okay. And again, the torus fixed points are going to be matrices that only have zeros and ones, and such that each column has exactly one in it. So the torus fixed points there should again be 6 of them. So for example, this matrix represents a point in my space. Actually, let me just explain this a little bit further because maybe the matrix isn't so enlightening. Sorry, and I forgot to say this is n equals 3, k equals 2. Yeah, let me just start this example over. Okay. So simplifying to the n equals 3, k equals 2 case, my nilpotent matrix pictorially is given by, so I have 2 rows and then n minus k plus 1, 2 columns, and then I fill it in with vectors, e1, e2, e3, e4. And I declare my nilpotent operator to move everything to the right, and everything on the right edge falls off to 0. So NE3 is E1, NE1 is 0, NE4 is E2, NE2 is 0. Or if you like as a matrix, so E1 goes to 0, so that column is just 0. NE2 is 0. E3 goes to E1, so I have a 1 in that position. And then E4 goes to E2, so I have a 1 in that position. And an example of a flag in this space could be built up by saying, okay, let V1 be the span of E1. Let V2 be the span of E1 and E2. And let V3 be the span of E1, E2, E3. And we can check the conditions. First, I need NVI to be contained in VI for all I. So for example, when I hit V1 with N, I just get 0 because E1 goes to 0. So that's certainly contained in V1. NV2, well, if we can look at this diagram. Well, E2 falls off the diagram. E1 falls off the diagram. So I'm just getting 0, which is certainly contained in V2. E1, E2 fall off the diagram. E3 goes to E1. So NV3 is the span of E1, which is certainly contained in V3. And essentially the rule, if you were to consult this, if you were to keep consulting this diagram, essentially the rule is in order to have NVI be contained in VI, we need to build up the flag from right to left along each row. So I couldn't just skip to V3 as my line because if I were to act by N on it, I would get E1, which is not contained in that line. So I have to start with the kernel and move left. And the second condition, so the first condition checks out, and the second condition is that we need V3 to contain the span of the vectors in this column, the kernel. And since we also included E3, that's also true. Okay. And so now kind of the trick is we should be able to write down all of the torus fixed points without even having to write down the subspaces. You just work from right to left in each row. So so I have the matrix given by E1, then E2, then E3. Or the way I might pictorially represent this is by recording in which order did I pick up these vectors. So first I picked up E1, then E2, then E3. And so I can turn this into the diagram 1, 2, then 3. Another way to do this is, say, start with E1. Once I have E1, then I can move to E3, and then I can pick up E2. So I could do E1, then E3, then E2. And the order in which I picked up these vectors was, okay, first E1, then E3, then E2. Um, um, or I could start with this diagram, like 1, 2, 3. That would correspond to E1, then E2, then E4. And I turn it into a matrix, E1, then E2, then E4. Or 3, then 1, then 2 would tell me the recipe that, okay, first I start with E2, then I go to E4, and then I go to E1. Or 3, 2, 1 would be the matrix E2, then E1, then E3. And then my final diagram would be 2, then 1, then 3. Sorry, let me clean this up. 2, then 1, then 3, which would correspond to the matrix. So first I start with E2, and then E1, and then E4. Okay, and this is exactly the set of row strict labeled rectangles that I wrote down before. Okay, so there's these bijections between torus fixed points and the combinatorial objects, and that was essentially the original motivation for looking at these varieties, but I want more information from them. In particular, I'm interested in Poincare series, being able to compute Poincare series, and matching it with the combinatorics. So given a complex variety, its Poincare series is the generating function you get by computing the cohomology groups and then turning those into the coefficients of a polynomial. And here I've halved the degree of Q just for convenience, notational convenience. And in order to compute these Poincare series, you can find what's called a cellular decomposition or affine paving of your variety. So in affine paving, I might actually, we're almost out of time, so I'm trying to figure out what should I skip here.
Well, we have one, we can have like one more lecture, so you can, if you want, you can continue from here next time, like instead of skipping. It's up to you.
Okay, let me skip to the upshot, and then next time I'll explain more how to get there. Um, yeah. So yeah, let me just skip to so computing the torus fixed points was the motivation. But what I'm really interested in is computing these Poincare series. And it turns out that the Poincare series of both of these varieties, so of both the Pawlowski-Rhodes space and these delta Springer spaces, matches a polynomial you get by taking the combinatorial formula in the delta theorem and just restricting to area 0 p standard terms and keeping track of the q degree. So it matches the polynomial, the q polynomial obtained from this delta symmetric function after basically after setting t equals 0 and taking the coefficient of m1 to the n. And so the theorem is, yeah, the Poincare series of P, R, and K is the sum, sorry, let me give myself some room here, is the sum over these word labeled Dieck paths with area 0 and standard labeled, where you keep track of the diagonal inversions up to a minor a minor alteration. So instead, you have to reverse this polynomial as a Q series. So what I mean by rev Q is take your polynomial in Q and reverse the sequence of coefficients so that if you have a polynomial of degree d, the top coefficient becomes the constant coefficient, and the constant coefficient becomes the top degree coefficient. And I'll explain in a second why this reversal is happening. So this is Pawlowski and Rhodes. Together with Levinson and Wu, we also realize this as the Poincare series of these delta Springer varieties. And essentially what happens is, like, why do you have to reverse? Essentially because Poincare duality fails in both instances. So Poincare, let me just copy and paste this. So Poincare duality says that if a complex variety is both smooth and compact, its Poincare polynomial is equal to its reversal. And the reason why I had to apply this reversal was because this polynomial is not symmetric. And essentially these Poincare series are computing the reversal rather than the polynomial itself. And so we're seeing two different failures of this Poincare duality because the Pawlowski-Rhodes space is a smooth but non-compact model. Whereas this delta Springer space is singular but compact. Or, compact but singular. Okay, and then what I want to explain, well, I'll maybe keep going with the examples, but ultimately what I want to explain next time is how to use Springer theory to construct a symmetric group action on the cohomology of this delta Springer fiber space. So that the symmetric group character you get is related to the delta theorem symmetric function, and also give new formulas, or a new formula for this delta prime ek minus 1 en. In particular, it's Schur expansion. Okay, so thank you. Sorry for going a little bit over time.
All right, well, let's thank our speaker. Very good. Any questions for Sean now? Oh, by the way, as we mentioned before, it's this question and answer session could go on for a while, and so people are welcome to stay or go as you will, of course. Anyway, any further comments?
I think there are two questions on the chat.
Mhm.
So the first one is like, how does torus fixed point help with computing the Poincare series?
Yeah, so this is the part that I just didn't get to, is so the torus fixed points, the way that I compute the Poincare series is to so decompose or stratify each of these spaces into a union of cells. And each cell gives a term in the Poincare series. But then each cell corresponds, like each cell contains exactly one torus fixed point. So that's why the terms are in bijection with these combinatorial objects. It's because the torus fixed points are in bijection with the combinatorial objects as well as the cells.
And Thank you. There's a second question asking you if you can show a few examples of the Poincare polynomial, but I think you will be doing that for in the next lecture.
Yes. But let's say hopefully I remember this correctly. That yeah, for n equals 3, k equals 2, then the two Poincare polynomials are the reversal, no. The two Poincare polynomials are 1 plus 3q plus 2q squared. So this is saying that there's one zero-dimensional cell, yeah, one zero-dimensional cell, three one-dimensional cells, and then two two-dimensional cells in the affine paving. And then if you reverse it, you get this combinatorial formula. So this is reversal of 2 plus 3q plus q squared, which is this is the combinatorial formula in terms of these labeled deep paths.
Here's
Does
a question
go ahead.
in this chat. Does the dimension of the cells correspond to a nice statistic on Fubini words?
Yes. You could translate it in terms of Fubini words. I don't know if I remember how to do that. I always compute them. Yeah, I never compute them in terms of the Fubini words. Somehow, for me, computing them in terms of inversions in these diagrams are somehow easier for me than doing it in terms of Fubini words, but you could translate it into Fubini words.
Okay, well, if there's no further questions, let's thank Sean again. Good.
Thanks,
And
everyone.
we'll see you all on Tuesday.
Thank you.
Thanks
Bye.
so much. Bye.